Hello, everyone. Good afternoon. I hope you can hear me. I'll wait for a second to get a response on the chat window. Thank you. Great. So good afternoon, Bangalore. I'm absolutely delighted, and thank you very much to the organizers for asking me to give this talk. I'm very sad not to be there in person. I'm 9 months pregnant, so I'm hoping that I won't go into labor during the talk. I also wanted to explain why I might seem breathless or out of breath during the presentation. But yeah, I really wish I could be there with you celebrating the momentous occasion of LIGO India's approval. So slide 1 and then slide 2. Ajit asked me specifically to talk and give details about the localization and EM follow-up of the gravitational wave transient GW 150914. So on slide 2, I'd like to remind you that the main characters in this talk will obviously be GW 151409, plus the LIGO detectors, as well as 25 EM partners, which comprises about 1,500 authors, and a lot of the results that I'll be detailing are expressed and shown in this paper, the localization and broadband follow-up of the GW transient, GW 150914, that's available on AstroPH and was submitted to AppJ Letters at the end of February. So a lot of the figures are detailed there. So slide 3. So the plan of this talk, so I would like to give a very brief introduction to GW EM astronomy, and in part 2 to really focus on this case study, the EM follow-up of GW 150914, and to discuss sort of the lessons learned and the future steps forward in terms of EM follow-up of gravitational wave events in this exciting new era. So slide 4. So coming to the introduction and of EM-GW astronomy, let's go to slide 5. So as you've all heard, last September, a wonderful surprise occurred when a strong signal was observed at LIGO Livingston and Hanford 4 days before the official first science run. And within hours, folk like Sergei Klimenko and others working in the search were able to characterize the recognizable chirp or roar from the frequency time plots as due to a binary black hole merger with total mass above 70 solar masses. So coming to slide 6, so this was visible literally within hours of the events. We knew that we were looking at a binary black hole merger. And coming to slide 6, and so for these stellar mass black holes, the general consensus was and is that no electromagnetic counterpart is generally expected for these systems unless they're in highly dense magnetized plasmas or in extremely gas-rich environments. So both the fact that the signal came as a surprise, and it was our first potential GW detection, the fact that it was a binary black hole merger dictated a lot of what subsequently happened in terms of EM follow-up. So I'd really like you to bear that in mind for the rest of the talk. So slide 7. So it's important also to remember that lots of electromagnetic partners or observatories that had signed agreements with the LIGO Virgo scientific collaboration for several weeks assumed that the trigger was associated with a traditional high-frequency gravitational wave source with electromagnetic parts. So here, I'm talking about neutron star binary mergers where at least one compact object is a neutron star and has some matter associated to it, or, for instance, a supernova. And the important thing to remind ourselves when we're talking about electromagnetic counterparts is that they're due to the delayed matter or plasma outflows during the merger or core collapse. And these are what are responsible for the electromagnetic counterparts that we observe at different wavelengths and different time scales. So if I'm going, for the rest of the next few slides, I'm going to focus now entirely on neutron star binary mergers, because this is what a lot of our electromagnetic telescope partners assumed the event was for several weeks. So really sort of dictates what the observations that they actually took for the event. So slide 8. And so for neutron star binaries, we expect to see two types of matter outflows. Broadly speaking, the first one comes from tidal tails and disk winds, shown at the top, where the ejector mass can vary from 10 to the minus 4 to 0.01 solar masses. And the second are ultra-relativistic mass ejections in the form of jets. So, sorry, I just saw there was a chat window. Is there a question at the moment? Okay, great. And the second are from ultra-relativistic jets. And the important thing to note is that here, the flow's kinetic energy is generally converted into internal energy. So it expands, the outflows expand, cool, and are heated by either shocks or by radioactivity. So coming to slide 9. So broadly speaking, for neutron star, neutron star black mergers, sort of the traditional GW sources with EM counterparts, we expect 4 electromagnetic counterparts. Firstly, a prompt radio emission that happens just for merger due to the growing magnetic field associated with one of these neutron stars, and the differential rotation will result in some relativistic plasma outflow and can be potentially seen as a sort of fast radio burst. The second are short gamma ray bursts. So they're essentially have accretion onto some centrifugally centrifugally supported disk, which is powering some relativistic jet. And we happen to observe this if we are lying in the barrel of the jet. The third counterpart are these optical near-infrared isotropic kilonova or macronova. These are essentially weak transients which are powered by rapid neutron capture nucleosynthesis in some initial neutron-rich ejector that's thrown out from the system. And so, a tremendous amount of effort has now gone into actually observing these. And the fourth is eventually this unbound ejector will slam into the interstellar medium and create synchrotron blast waves, which are then detectable slow radio remnants. So these are sort of the time scale shown in this cartoon figure that I've plotted out of the electromagnetic counterparts. Now, there are several things I'd like to stress which are important in terms of even understanding what was the follow-up taken for GW 5914. So if you go to slide 10, firstly, these EM counterparts have very different observable timescales. The radio emission we can expect from seconds to minutes, and their longer radio counterparts from months to years. In terms of the optical infrared kilonova, we can expect these events to shine or be detectable on the hours to days timescale, modulo the modeling uncertainties. Going to slide 11, these electromagnetic counterparts also have very different emission geometries. For instance, short gamma ray bursts, we only happen to detect if we're lying sort of in the barrel of the beamed jet and their subsequent afterglows. Whereas the other electromagnetic counterparts are thought to be much more isotropic. And the third important factor is that we have obviously observed short GRBs. A lot of these other counterparts, we have either got very interesting candidates and we think that we've seen them, but we don't have any smoking gun confirmation. And this is really because we've entered this renewed era of time domain astronomy in the optical and the radio bands. So this really stresses, the different properties of these electromagnetic counterparts. And specifically, I want to stress the emission timescale. So this really determined what happened in terms of observatories looking for the counterparts of GW 150914 before they knew it was a binary black hole. Now, slide 13 comes to this important question of why we actually even want to have gravitational wave and electromagnetic measurements. So on the left-hand side is a box that shows the sort of parameter measures that we hope to measure from the gravitational wave chirp, and indeed have in the case of GW 150914. So the masses, the spins, potentially the neutron star radii, as well as the geometric properties of the event. And then coming to the last talk and the question that we heard there, what can we actually learn from the electromagnetic spectrum signatures? So for instance, we'll have some information about the ejector and the velocity, potentially the magnetic field strength, an accurate position or the redshift, as well as from spectral measurements, the nuclear physics of actually the composition, potentially these kilonova or these R process powered transients, optical transients. And so, of course, it's really by combining all this information that we can actually put these neutron star mergers in their full astronomical context. And this is really sort of the next step, is understanding how we can do this. And so slide 14. So the aim is, of course, not just to have a strong signal binary and to do sort of full characterization of these systems in terms of really getting very good measures, for instance, on the neutron star radii. Also, we're really looking into this new era where we're talking about having potentially tens of events in order to really study the demographics, ecology, and census of these events. So I really want you to sort of bear that in mind as sort of the overall science motivation for why we want to actually do GW plus EM astronomy and where we're sort of heading. So let's go to slide 15. So now I'm really going to come back to GW 150914, exactly how it provided us with a practice run for doing electromagnetic follow-up observations and really going after the electromagnetic counterpart of gravitational wave mergers. So let's go to slide 16. So going back to last September, shown here is a timeline of the electromagnetic follow-up on the horizontal axis, showing the time with respect to merger from hundreds of days to obviously when the event happened. And the blue, green, and red bars show the observational epochs that were taken by different telescopes in the high energy, optical, near infrared, and radio bands. So really just to show you, there was a great diversity, and obviously the horizontal axis shows the span of sort of the time of different epochs that people went and actually observed various parts of the sky that were localized by GW 150914. Slide 17. And the top bar shows the actual announcements that we, the LIGO Virgo collaboration, sent via gamma ray, the GCN, GW Alert GCN, so this is the gamma ray coordinate network, to MOU EM partners that had signed agreements with the collaboration. And there were three important notices that were sent out. The first one, the first set of sky maps was sent out 2 days after the event. The second announcement, the fact that it was actually a binary black hole candidate, was sent out 3 weeks after the event. And the third announcement, the final sky map, was sent out 4 months after the event. So this is quite critical in understanding what happened in terms of the EM observations of this event. And I'd really like to stress that the fact that a lot of observatories assume that it was a neutron star binary or even a core collapse supernova really dictated how deep they looked, as well as in what parts of the sky they looked for the 3 weeks subsequent to GW 150914. Now, slide 18. So coming to the actual sky maps here, I remind you that localization with 2 detectors really critically depends on the time of the arrival of the signal at each detector, as well as the antenna functions of the detectors themselves. So shown in the light blue and blue are the sky localization contours that came from the unmodeled burst searches that were sent out a couple of days after the event, from the continuous wave burst, which localized the event to 310 square degrees, and the LAL inference burst, which localized the event to 750 square degrees. And you can see that there's a significant patch in the northern hemisphere that was both these searchers sort of identified in their initial runs. The dark green contours show the LAL inference sky maps, which localize the event to 590 square degrees, which in some sense is the most accurate sky localization map that we have of the actual event. It takes into account calibration uncertainties as well. And just to stress that the annulus of these sort of rainbow arcs is really determined by the arrival time between these 2 detectors. So I really would like to emphasize that initially, the first sky maps did suggest that a large portion of the northern hemisphere, there was a significant amount of sky area in the northern hemisphere. So coming to slide 19, on the right here now plotted actually shows the improvement that we can expect, and these are preliminary results from the collaboration, if you include actually Virgo, where you can potentially see a factor of 10 improvement with the green blob, which is really difficult to see, I can see. And then actually a further improvement then of 1.2 if you include LIGO India. So this really emphasizes why you want to have more detectors in your network to really be able to localize these sources, so we're not talking about these huge hundreds of square degrees uncertainties. Now, going to slide 20, shown here, overplotted on this 590 square degrees, are the observational footprints of different wave bands, telescopes in different wave bands. So in red is the radio, in green are the optical infrared footprints, and in blue are the high energy footprints. And so if you look in the insert of this figure, you can see, for instance, the Swift XRT, very, very small field of view, sort of hexagonal plots. But this was indeed the amount of the localization areas that Swift itself covered. And so you can really see a huge diversity in the waveband coverage. So for instance, the radio in the red big sort of circular blobs. I wish I could point to you in person, but you can see, really covered vast areas of the sky. And also I'd like to stress that there's 19 orders of magnitude in frequency space in the EM spectrum that were covered for this event. So a significant fraction was, but obviously a lot of telescope time was also spent in the northern hemisphere patches from the initial sky maps that we sent out. Slide 21. And of course, this happened as a function of time. So sky coverage was not done sort of, as soon as the alerts were sent out, but really observatories, trying to sort of fold in information that they know about the electromagnetic emission from various counterparts really dictated when they took their epoch observation information. So coming to slide 22. And so very nicely in the LBC paper of the localization and EM follow-up is a table that really summarizes the wide field synoptic surveys in terms of the depth and the area covered of the various sky maps. So on the very right is the contained probability that was covered, the percentage of the different sky maps coming from the burst as well as the LAL inference pipelines. And there's also a column, for instance, on the depth. Now, it's a very busy plot, so what I really want to stress is just for you to take in the number of different facilities that actually, and different wave bands that actually followed up GW 150914, some with very, very different sensitivities. So if you focus on the optical, for instance, which is the third sort of set of instruments, the telescopes involved had apertures from 1 to 4 meter classes, and 36% of the LAL inference sky map was covered by these events. And a third of these facilities actually went ahead and targeted first galaxies that they assumed were in some gravitational wave detectable distance of these events. Now, in the X-ray, for instance, SWIFT, and you remember the SWIFT covered a very small part of the sky, actually went up and targeted 5 galaxies, which they assumed were quite close by, in order to, assuming that some sort of merger event happened within or nearby a galaxy. And if you go to the radio, which is the very bottom sort of set of information, 86% of the sky map was covered by MWA, for instance, whereas only 0.1% was covered by LOFAR in the northern hemisphere of the final LAL inference. But they have very different sensitivities in terms of the depth that they can actually reach. So I'd just like to stress that, there was this whole host of wide field synoptic instruments that went after the event. Now coming to slide 23, and of course, shown in this figure here, we're looking at this 590 square degrees in the southern hemisphere. I remind you that the full moon itself occupies 1/4 of a square degree. So we're really talking about this huge swath of sky area that we were able to localize W 150914 in. And within this area, there are many, many other transients and variables, particularly in the optical. In the radio, we're only now beginning to understand what other transient and variable sources are there. But several spectroscopic facilities shown in the table here actually went after several of these candidates. So you can see that the candidate number would vary from 8 to 9. And typically these 8 to 10 and 1 to 10, and typically these candidates spanned supernova type 1As and 2s, active galactic nuclei, as well as galactic transients and variables such as dwarf nova. So spectroscopic instruments did go after candidate events that happened within this 590 square degrees. And the comparison, in order to actually determine not only that these were extragalactic and galactic transients, but the comparison with the distance and the GW redshift is critical. And in order to learn more about the actual other transients that were seen, I recommend that you go to the EM companion partners, such as the ones I've listed in the bottom right, from SWIFT, Pan-STARRS, IPTF, the dark energy camera. But really to stress that there's a lot of other science and other interesting astrophysical sources that you can observe even when going after the gravitational wave counterpart. So coming to the next slide, which is slide 24. So indeed, for GW 150914, there was no reported real-time observed EM counterpart, although de facto, so after the event and going back to the data stream, the Fermi GBM reported a sub-threshold event above 50 kV, 0.4 seconds after GW 150914 event was actually detectable, with a false alarm probability of 0.002 and lasting 1 second. However, I'd really like to stress that though we have this temporal coincidence, we still don't necessarily have, obviously, a good still coincidence. We're talking about 600 square degrees. Although it's interesting to note that if it was actually a counterpart if it was an electromagnetic counterpart to GW 150914, just using this Fermi GBM information would have shrunk the error box to 200 square degrees. So we wouldn't have had a precise localization, but it may have helped. But it really is, I think, the community and the result is still sort of discussing whether this was actually a possible candidate. But, interestingly, following the actual announcement of this event, suddenly there was a slew of theoretical astrophysics papers actually proposing models for electromagnetic counterparts coming from black hole mergers, really, I think, emphasizing the creativity of theorists. And so I've just listed a few of the papers down below, but I think all of them really suggest that the likelihood of seeing a counterpart is extremely low. You really do need to have very rarefied conditions, huge amounts of gas or highly magnetized plasma in order to even detect something. But just to stress that I think until we actually do the exercise and observe and see whether there are potential counterparts to BBH, it's a really exciting and open area of research and questioning. So coming to slide 25, so sort of what next? What's going to happen, as I see, in sort of the next 5-10 years, especially with LIGO India and other wide field synoptic surveys coming online. So I know Varun will be talking next about really exciting optical and radio initiatives that are taking place in India itself. I would like to mention that in 2017, there will be a Dutch effort to actually build a dedicated optical telescope to go after every single gravitational wave merger trigger. So this is not just applying for target of opportunity time, but this telescope has been designed specifically to trigger on every single gravitational wave event that will be released by LIGO, Virgo, CAGRA, and others. And it will be built in Chile, in the La Silla site, and we should potentially have a field of view of 9 square degrees to maybe 40 square degrees, and go relatively deep and have several different color filters. And excitingly, the prototype is actually built at the moment in South Africa and will be online this year, which will be slewed to Meerkat to look at the contemporaneous optical and radio skies. So please contact me if you'd like to hear more details, or my colleagues at Radboud about this initiative. Now, slide 26. But I also want to spend a bit of time talking about, sort of the prospects of detection, for instance, with LIGO India coming online in the early 2020s. We're not increasing the gravitational wave detector network. We're not necessarily talking anymore about hundreds of square degrees, and relatively close by events, but we're also talking about really shrinking those error boxes down to sort of tens of square degrees. And this is when it becomes, and also looking sort of much further out in terms of the distance. So this is when it becomes very exciting for sort of the prospect of many other wide field synoptic telescopes that are coming online in the optical and in the radio. So shown here in this is the relative percentage of detectable optical counterparts that we may see using 1 meter, 4 meter, and 8 meter class telescopes from a simulation that I ran of neutron star binaries that were detectable with 5 gravitational wave detectors, including LIGO India. And what I'd like to focus is that with 8 meter class telescopes, such as the Large Synoptic Survey Telescope, you can potentially, and obviously this depends on the northern southern hemisphere coverage and weather, etc., but you can potentially detect all of these electromagnetic counterparts, coming back to the previous question in the previous session. So it's a really, really exciting time where I think, we are talking about having the instrumental capabilities on both the gravitational wave and the optical and the radio to actually ensure that we can see sort of multi-wavelength EM and gravitational wave emission for these emergers. So coming to slide 27. So one thing sort of looking forward now in terms of strategies that we can do is actually to talk about not just sending out information about the sky area, but also distance information. So shown on the left here is a plot from the similar MCMC simulations that I ran, which show the gravitational wave volume as a function of luminosity distance for different neutron star binary mergers that were detectable with a 3 GW detector network with LIGO and Virgo. And what I want to, and shown in the horizontal lines are sort of the distance measures that we can actually estimate. And this was really nicely presented in a paper that was posted a couple of weeks ago by Leo Singer and others, where they show very nicely quick methods in actually estimating the distance to send out this information, so that we actually know something about how far the system or how deep these various telescopes have to actually look and stare in order to see the neutron star merger. And this has a consequence if you actually cross-correlate your gravitational wave volume, coming to slide 28, with a galaxy catalog, assuming that the merger happened within or nearby different types of galaxies, either star-forming or red elliptical galaxies. And so shown on the left, actually, a public SDSS GW galaxy catalog that was produced with photometric redshifts with a postdoc produced by myself and a postdoc at Johns Hopkins University, which is now actually available. And so please, feel free to go and actually use this catalog, which goes out to a redshift of about 0.2. So significantly further than the horizon distance that we're talking about. And shown on the right are the number of galaxies the number of brightest galaxies that produce 50% of the light as a function of distance of the gravitational wave merger that we expected from the years of 2015 to 2016 and 2017. And this was in a nice paper led by Neil Gerrels and John Canizaro that we posted last year. And so what I want to stress in this is that we expect to see about that we need to perhaps follow up about 25 galaxies using not just the sky area diminishing due to including, for instance, Virgo, but also using some information of the distance, the horizon distance, GW detector networks. So going after 25 galaxies, or, as we saw in the case of GW 150914, was actually possible for something like SWIFT, the SWIFT XRT instrument. This is something that they can do within a couple of nights observation time. And by doing this cross correlation, you can reduce the false positive transients by a factor of tens to hundreds. So just to summarize now, the conclusions and I think the lessons that we can take forward from this first practice run, it was an extremely positive and heroic multi-wavelength effort using a huge variety of synoptic and spectroscopic capabilities to follow up this event. But now, sort of from the electromagnetic side, I think it's very important that our partners are actually prepared to follow up binary black holes and neutrons black hole mergers beyond this 200 megaparsec horizon distance that we've often talked about. So, for instance, to actually prepare and produce galaxy catalogs out to much larger redshift. And I think from the gravitational wave side, it's important to talk about actually releasing information as much as possible in terms of the sky position and the distance, and potentially any actual progenitor information, the masses and spins of the system, which will have an impact on how bright the EM counterparts will look like. And also to make sure that on the EM side, we really begin this comprehensive and systematic study of the transient and variable skies. So I'll end then. Thank you for taking the time.
Thank you very much.